I would like to very much thank the organizers for the invitation to give a lecture here and for the honor to be the open lecture of the conference. This means very much to me. Thank you very much. And today I will speak about shortwave asymptotics for equations with specially localized right-hand sides. And by way of example, we consider the simplest system of Maxwell equations. What I will be speak about in this talk is joint work with Sergei Dobrokhotov, Anton Tolchenikov, and in fact some other members of the Laboratory of Natural Hazards at Moscow, at Institute for Problems in Mechanics. Well, so let's start. Well, we study asymptotic solutions of equations with localized right-hand sides, and for example, we use this system of Maxwell equations, the simplest here. Here we have p hat is minus IH nabla, omega hat is minus IH d over dt. So we have this equation. H is a small parameter, for example, the reciprocal of the wave number. And here we have special inhomogeneity. The speed of light velocity depends on x, and also we have time dispersion in that we have not omega square, but rather some function of g of omega. Well, and here we have time-dependent right-hand side, which is localized in the neighborhood of the origin. V of yt is rapidly decaying for large y. Well, and so if h is the small parameter, this function is localized in the neighborhood of the origin. In fact, the very same equation, but without right-hand side and rather with localized initial data, was considered in a paper by my co-authors, Dobrokhotov and Tolchenikov, here in the mathematical paper. Well, and before we proceed to this example, on more precisely to what happens when we have systematic equations and some specific features, I will discuss the scalar case, how to construct asymptotics for equations with small parameter and localized right-hand side. So we consider this sort of equation. HU is F in Rn, where H is a pure differential operator with some symbol and with a small parameter multiplying the derivative. Well, and for example, we can cite Helmholtz equation and water waves equation. Here are the corresponding symbols. And the right-hand side is localized near some point x naught, is rapidly decaying. So in fact, if we take the right-hand side to be the Dirac delta function, then we just obtain the fundamental solution of Green's function. Well, and it might seem that to solve problem with any right-hand side, it suffices to find the Green function and then compute the convolution. But this is not always convenient, because if the right-hand side itself is rapidly varying, then the convolution is in the integral with rapidly varying integrand, and it may be harder to compute, at least in the many-dimensional case. And so if we have a method to construct asymptotics directly, it would be preferable. So we can discuss just such a method. And the first thing we should speak of is that the solution of such a problem is, as usual, non-unique. So we must have some condition which singles out a unique solution. So, for example, in many problems, one uses the limit absorption principle. And it is as follows. If, say, our operator is self-adjoint, then we consider this equation with a small parameter epsilon. and then consider the limit as epsilon tends to plus 0 from the positive side, if the limit, of course, exists and the limit is local in X. For, say, for the Helmholtz equation, the solutions of these equations lie in L2, but the solution of the limit equation does not lie in L2, so we only have local limit. Well, our problem is, however, different. We wish to find asymptotic solutions, and we don't know, and in fact don't care about exact solutions. This is entirely different topic. So we asymptotic solutions are not unique, and so we single out some solution by some sort of asymptotic limit absorption principle. So we consider this equation, construct a asymptotic solution, and then take the limit as epsilon tends to 0. This may be used as a version of the definition, but the existence of an asymptotic solution in this sense does not imply the existence of the exact solution, of course, and even if the exact solution exists in the sense of the limit absorption principle, then it is not clear in the general case whether the limit asymptotic solution is asymptotic to the limit exact solution. We do not study this question here. It is a separate, very difficult problem, and of course it cannot be solved in the same generality as the construction of asymptotic solutions. When constructing a asymptotic solution, we generally do not care very much about the behavior of the symbol of our operator at infinity in the momenta. While if we deal with exact solutions, this is perhaps the most important consideration. So once more, here we consider only asymptotic solutions and do not make any claims whatsoever as to how these solutions are close or not close to exact solutions, or whether the exact solutions exist at all. Okay. So the right-hand side of this form can be represented via the Fourier transform of the function f. And in fact, this expression is none other than the expression for the Maslov canonical operator on the Lagrangian manifold, which is as follows. It is the vertical plane at the point x0 in the phase space. So x is x0 and p is arbitrary. And the delta function, of course, can also be represented in this form with unit amplitude, but we are not interested in that. Instead, we consider rapidly decaying smooth functions. So also, the method we will be discussing permits considering equations of this form, where the right-hand side is not a localized function, but rather a function represented by Maslov canonical operator on an arbitrary Lagrangian manifold. But here we restrict ourselves to this simplest case. So here is some history concerning the equations with right-hand sides. Well, okay, so I will not dwell on it possibly. And so the mathematical statement of the problem is as follows. We need to construct a asymptotic solution of this equation as h tends to 0, and we make some assumptions about the Hamiltonian h of xp of this operator h. These assumptions are as follows. The first assumption is that the symbol, the absolute value of the symbol, does not decay too rapidly at infinity. This is a very, very weak analog of elliptistic condition. In elliptistic condition, we will have not minus n, but rather m here, where m is the order of the operator, but here it appears to have this. And this is in fact somewhat technical condition, and the main conditions are the following. We consider the solutions of the Cauchy problem for the Hamiltonian system, and we consider the trajectories which issue from the set L0, which is precisely the set of those Q in Rn where h of psi q is 0. The set of zeros of the principal symbols intersected with the initial Lagrangian manifold with the plane over the plane x equals to psi. We require these solutions be defined for any t, any positive t, and we require that there is no trapping condition. For each compact set in the x plane, the trajectories leave this set in some t. So we take an arbitrary r, and the trajectory leaves, the x component of the trajectory leaves the ball of radius r in some finite t. So the trajectories are going to infinity. Well, okay. So in the idea of the construction is in fact very simple. Consider the auxiliary Cauchy problem of this form. We add new variable t, and as the initial data, we pose our right-hand side. Then the solution of this equation with the right-hand side can be written in the form of this integral. Of course, this is a purely formal procedure because the integral diverges. However, if instead of v, we take an asymptotic solution of this problem, then we can somehow modify this integral so as to ensure convergence. And the modified integral will be a asymptotic solution of our problem. This is possible precisely because the non-trapping condition is in force. So, informally speaking, if we seek our solution for x in some ball of radius r, then this integral need not be from 0 to infinity, but only from 0 to some t naught, after which the projections of trajectories leave this ball and have no impact on the asymptotic solution here. So this is in fact, a very simple idea. Well, okay. Well, I would like to give some very short reminder on the canonical operator. So if we have a Lagrangian manifold, it can be defined in terms of some non-degenerate phase function, as written here. Well, and then the canonical operator can be given in the form of this integral. So it is, the details are not very important here. The most important thing is that we have this rapidly oscillating integral, which represents the canonical operator. Okay, and then the canonical operator is patched together from these local expressions with the use of some partition of unity on the Lagrangian manifold. Okay, so what precisely is the Lagrangian manifold which we use in this problem? Well, so let me, in fact, make some drawing here. Here we have the configuration space Rn, and here we have the point psi, the point psi, over which our function is localized, and here the initial plane, which is we denote by lambda naught. And so we issue the trajectories, and the union of these trajectories gives us a Lagrangian manifold lambda in the extended phase space, if we include also t and the dual variable E energy. Well, so we also have here a set. Well, this is not lambda, this is perhaps L. This is the set lambda naught. Lambda naught is the set where h of x, f of psi q is 0. This set is necessarily compact in view of the first condition. The Hamiltonian is non-zero at infinity. And so we have this tube which issues from this lambda naught. And this is the most important part of our construction. Well, okay. So let's discuss this further. Well, the first theorem says that if the support of the Fourier transform of the right-hand side doesn't meet this lambda naught, then the solution is actually the same as if the operator were elliptic. We just divide by the principal symbol, and this will be the Fourier transform of the asymptotic solution. Well, so if, however, we have a right-hand side with compactly supported Fourier transform, whose support does meet this lambda naught, then the solution can be written in the form of this, this integral here, where chi is an appropriate cutoff function which makes the integral converge. So, okay. And if we have this additional condition that h, the derivative with respect to p of the Hamiltonian is not zero for the momenta here in lambda naught, then this means this tube is a smooth manifold, and we also have a Lagrangian manifold, well, okay, lambda plus, which formed by the trajectories issuing from this lambda naught. We denote this manifold by lambda plus. Lambda plus is a subset of R to N, not of the extended phase space. And the asymptotic solution outside of the point psi is given just by the canonical operator on this manifold plus. Well, okay. So this is basically the same picture that I have drawn here. Well, okay. And here is the most special case in which the right-hand side is the canonical operator. And the only difference will be that our condition will not be that HP is non-zero on the lambda naught, but rather that the Hamiltonian vector field is not tangent to lambda naught. So if we have a manifold, isotropic manifold lambda naught of dimension n-1, and the Hamiltonian vector field is not tangent to it, then the Hamiltonian flow is a Lagrangian manifold. That's basically what this condition needs for. Okay. Well, now let's proceed to our example of Maxwell equations. In this case, for these simple equations, the principal symbol has this form. Well, and so we have matrix principal symbol, matrix operator, and so the asymptotic solution of this Cauchy problem here, auxiliary Cauchy problem, need to be constructed according to general procedure for systems of equations. In that we use the eigenvalues of this matrix as effective Hamiltonians, and we have these eigenvalues and asymptotic and eigenvectors of this Hamiltonian written here. And the difficulty is that, as is often the case, we have change of multiplicity of these eigenvalues at the point p equal to 0. Here is an important consideration. If we deal, as is in the theory of Fourier integral operations, with asymptotics with respect to smoothness, then only large values of p are important. It is not important what happens at p equal to 0. However, if we deal with the asymptotic theory, then we do not care very much about what happens for large p, and instead we need to do something for p equal to 0. So one has to consider more general Lagrangian manifolds, which are called punctured Lagrangian manifolds, and they are called punctured because they have some sort of holes on the plane p equal to 0. Well, these were considered in the papers written here. Well, here is a formal description, and I will maybe again give an informal description of this. In the theory of Fourier integral operators, one deals with homogeneous Lagrangian manifolds. If we have some Lagrangian manifolds, lambda, then and it contains a point xp, then the point x lambda p is in lambda for all positive lambda. Okay. So these are homogeneous Lagrangian manifolds, and they have some singularity at zero, at least in the derivatives. Well, and if we write a canonical operator with parameter on such manifolds, then this singularity at zero prevents us from constructing asymptotic solutions to an arbitrary accuracy. So we can say achieve the accuracy of O of h to the power of m, but not better, because when we construct subsequent terms of the asymptotic solution, they contain derivative with respect to p, and the singularity at p equals 0 becomes more bad, and so in effect you reach some accuracy, and then subsequent terms of asymptotic expansion do not add to such accuracy, but they do add in that we can differentiate our asymptotic expressions more and more times, still having O of hm in the right hand side. So these are for homogeneous Lagrangian manifold. In problems of asymptotic with respect to h, we can deal not only with homogeneous, but with asymptotically homogeneous Lagrangian manifold. As p approaches 0, they are represented by function, asymptotically homogeneous function. This is if we have such a Lagrangian manifold, we have first the manifold itself, and then its limit homogeneous Lagrangian manifold, which is obtained as p tends to 0, some sort of tangent cone, if you say. And these conditions, which are written here, just say that both manifolds are good Lagrangian manifolds. Not only the manifolds lambda cell, but also the limit homogeneous Lagrangian manifold. Well, so here the same, some conditions about the phase function corresponding to punctured manifolds. Well, let me omit this for brevity. And the class of punctured Lagrangian manifolds invariant under shifts along Hamiltonian vector fields corresponding to first order pseudo-homogeneous Hamiltonians. Here, where we have the second difficulty, because our Hamiltonian is of second order. And so, if we write this, if we write this solution, we will not obtain partial Lagrangian manifold. So, we pass to the Fourier transform with respect to this variable omega, and consider this equation as written here. Well, and then the solution formula becomes as follows. Here we have this formula. We make the change of variables here, and after this change of variables, what is written here is, in fact, representing a canonical operator on a homogeneous, on a punctured Lagrangian manifold. So the most important thing here is as follows. We had the condition that here is our manifold lambda naught, where the Hamiltonian is 0. If we need the trajectories to go to infinity outside any compact set. However, in this case, where we have change of multiplicity at p equal to 0, the trajectories leave the compact set in different times. the smaller is the momentum, the more time it takes the trajectories to leave the compact set. So this change of variables, as shown here, eliminates this difficulty. All trajectories in the new variables leave the compact set at the same time, and this way we obtain the solution. So here are some papers which discuss the previous results, and the paper discussing the results of the present talk is underway. And so I guess, so thank you very much for your attention.